All right, well, thank you all for joining to another lecture for Introduction to Computer Graphics. Today's lecture is going to be fun. Well, not like other lectures were not, but today's lecture I'm hoping is going to be particularly fun. We're going to talk about finally surfaces. Yay! That's going to be fun. So, it's going to be fun. I'm saying it's going to be fun because today's lecture is going to be sort of a light lecture. We're going to talk about how things are done in computer graphics. It's going to be a little more philosophical than the other lectures. It's going to involve less math. Well, there's going to be a little bit of math. Come on, this is a computer graphics course. I have to introduce some math, but not much math. It's going to be just a little bit. But most of it is going to be light. So sit back and relax. This is going to be not a very hard one, but hopefully informative nonetheless. All right. So, where do we start? Surfaces. What are we trying to do? What we're trying to do is to get some 3D models, like this guy. Remember this guy? Whoa. We've seen this guy when we were talking about 3D transformations, right? So, yeah, this is just an example of a model. So what's important here, and the reason why I'm showing this, I'm going to show you a few more models, is that this may look like something, but it's actually just a surface. It's just a 3D surface because that's what we do with 3D models. And it's not exclusive to this model. Anything we have in computer graphics, like, I don't know, this model, why not? Everything is just the surfaces that you see. But of course, when we look at this, what we perceive is something else, right? What we imagine that this is, especially if it's realistically prepared, when we look at this, what we imagine is something that actually has some substance in it. Because that's how it is in reality. Objects have some substance in them, have some material in them. But in computer graphics, we don't necessarily care about what's inside because we don't really get to see what's inside most of the time, right? We just get to see the surface. And this is an important point. Now, I'm going to spend a little bit of time just talk about this very, very simple concept because I think that sort of sheds a light on how things are done in computer graphics and what computer graphics is all about. Like, imagine, for example, a character like this. Now, do you think this character has a skeleton? Well, actually, probably, because we use skeletal animation and we sometimes put some skeleton in the model so that we can animate it nicely, but not necessarily a detailed skeleton like this, but something that resembles a skeleton may exist. Okay, skeleton, maybe yes, maybe. But how about a brain? Well, not a fully functioning one at least. Well, you could say, oh, I have some AI code and that sort of serves as this brain. Okay, whatever. But we don't really model this brain and put it inside its head, right? Unless your application is doing brain surgery to this guy, you're not going to model its brain, right? All right, you're not satisfied with brain. How about a stomach and the whole digestive system? Like, why would I do this? I am never going to feed this character, ever. So why do I need to model this, right? I obviously won't. I don't care. For a lot of things, I don't care. So why am I talking about this? Here's an important topic, and that's really general to computer graphics as a whole. In computer graphics, a lot of things that we do is representing reality in one way or another. And then reality is really complicated. There's so much complexity out there, so much hidden complexity and sometimes obvious complexity. And some of this complexity is entirely irrelevant. I simply don't care. And I will never care about this character when I'm using this character. I never care that it's lacking a digestive system, right? And there's so much details like this in reality. So don't think about computer graphics as a way of representing reality or our imagination as a whole. We're just interested in the part that's relevant to us in the way that we can perceive. That we're just interested in the visual part of things. And that distinction is very, very important. And it's not like we're trying to cut corners or we're trying to just trick things. We're just trying to, hacking things together. That's not the point. The point is that reality is immensely and unnecessarily complicated. You can even say that this is not a limitation of our current technologies. I would even say that a computer, a fictional computer that exists in some reality, cannot fully simulate that very reality with its whole complexity at real time. It just cannot do that. You have to draw the line somewhere. You have to simplify the reality. It could be actual reality, it could be some fictional reality. You have to simplify it so that you have enough computational power to represent it within a reasonable computation time. Right? So that's at the very heart of computer graphics. And because of that, when we're dealing with 3D models, we just represent their surfaces. We don't care about what's inside of them. We don't even try to model them. Of course, there are exceptions, like, of course, right, if you can sort of see through the character a little bit, yeah, maybe you model what's under the surface, or maybe you just model the appearance of what's under the surface, not necessarily what's under the surface, but just its appearance, right? So there are some exceptions to not modeling anything inside a model. But nonetheless, when we think about 3D models in computer graphics, we're talking about surfaces like balloons. It's completely empty. They don't have to look like balloons. I think about them like things like like this, right? This is my understanding of what a computer graphics 3D model is. It's just a surface, right? And I think it's a good mental model when you think about computer graphics models, right? So our topic for today is surfaces. So by surfaces, I mean 3D models. Last time we talked about curves, so it kind of makes sense that we're talking about surfaces today. All right, this is the whole philosophical part of this lecture. I'm going to move on and actually talk about surfaces now. All right, so what's a surface? How do I represent surfaces? Remember, when we started talking about curves, we said probably a good way of representing curves would be using implicit formulations, right? Well, we can do the same thing for surfaces. Why not? So that brings us to implicit surfaces. So I can define an implicit function like this, such that, in this case, x is just a vector. The solutions to that function can be a surface. Now, this is a very powerful notation. This is exactly the identical notation we had for curves, right? The only difference here is this function f here. So in this case, the function f, the solution to the function f, is a surface, not just a curve. And for representing curves, the function f was representing something that was a curve. For representing surfaces, that's going to be representing a surface in 3D or whatever dimensions that you're interested in. And this implicit formulation is actually very, very powerful, and you can represent a lot of interesting things with it. So what can I do with an implicit function? I can actually do a lot of crazy things. I can, for example, represent some fractals. Fractals can be written in a implicit function form. Some fractals, anyway. And you can render them and get some really interesting looking surfaces like this. And trying to model something like this with all its detail without using an implicit definition would be very, very difficult, actually. But we don't always render fractals. This sounds like something very why would you? Okay, some people are interested in rendering fractals, and they're doing that, but it's not like what we do in computer graphics every day, right? It's just something we can do, but we don't always do that. So implicit surfaces A lot of people think that they're not very popular. They're not really used all that often. And to some extent, they're correct. But to some extent, there are some implicit surfaces that we do use very, very often. Can you think of an example? I'll give you a second. Well, here's one. How about a sphere? Yeah. So we have a lot of ways of representing spheres or approximations to spheres in computer graphics, but nothing is as perfect as the implicit formulation. So the implicit formulation, obviously, what's the formula for a sphere? You have to remember x squared plus y squared plus z squared is equal to r squared, right? So if you can write it in implicit form, it will look like this, right? So this is a sphere centered at the origin. I prefer writing this equation like in vector form. In vector form, you can write the very same equation in this form. So this position dot product with itself minus the radius squared is going to be 0. So any point that satisfies this equation would be a point on the sphere. And that's actually a very, very convenient representation for a lot of cases. And we do use that, this representation, implicit spheres, a lot for all sorts of different purposes. And we do use them for rendering as well. We don't often use them for rendering on the GPU because GPUs are designed to render triangles and pretty much nothing else. But we do use them for other kinds of rendering operations, and we are going to use them. Actually, we are going to use implicit spheres in this course when we're doing ray tracing. So we'll get to that much later. All right. So sphere is one example. The other one, some of you mentioned in the chat, the other one is a plane, an infinite plane. An infinite plane is infinitely difficult to represent using anything else. But if you have an implicit formulation, an infinite plane is actually fairly easy to represent. So what's the equation of an implicit plane like this, an infinite plane like this, the implicit equation? Could be, if it's the surface normal is z, well, could be z is equal to 0. So any point with this that satisfies this equation would be a point on the xy plane where z is equal to 0, right? Of course, I don't have to, I can rotate this plane however I like, but I could maybe, look at this plane, right? In this case, the equation would be just any point that's dot product is equal to 0 would be on this plane. Of course, this plane, if this satisfies this equation, then this plane is going through the origin. If it is not going through the origin, then we can move this plane in this normal direction just a little bit, and the equation becomes this. Right? All right. So these are simple surfaces that we do use in computer graphics for all sorts of purposes: implicit infinite planes and implicit spheres. But these are not the only ones. There are typical examples of what we do use, but we do use them for relatively simple shapes like this. Although the implicit formulations, the implicit surfaces are not limited to this. You can actually pretty much model anything with implicit surfaces if you're willing to put enough time and energy to it. For example, this is just an example of an implicit surface, a particular implicit formulation that allows you to model surfaces like this. And there are others as well. So, back in the day, in the beginning of computer graphics, people experimented with this idea a lot because implicit representations had a lot of advantages. But trying to model something specific using some combination of, you need to write the correct equation to form a shape like this. And that's where things get tricky. If you're a mathematician, maybe you can figure that out. Or maybe you can build tools so you can sort of graphically put equations together that form a surface like this. This is exactly what's happening here in this case, actually. But this turned out to be not a preferable way of modeling things. So we don't use these kind of complex implicit models very often in computer graphics. These are actually very, very rare. Back in the day it happened, but nowadays we don't really use them. All right. So I want to go back to how we talked about curves. So when we talked about curves, we started with implicit formulations, and then we talked about parametric curves, right? And we talked about polynomial parametric curves. We talked about Bezier curves. And the equivalent, the surface equivalent of Bezier curves would be Bezier patches. So let's talk about them. So what's the Bezier patch? Let's start with the Bezier curve. So a cubic Bezier curve is a cubic polynomial curve, you'll remember. It's defined by 4 control points in space, right? So this is the control polygon connecting these 4 control points. And the curve, the Bezier curve, the cubic Bezier curve, defined by this Bezier control points would be this. So this is a Bezier curve. Now, this is a curve. From this curve, I'm going to generate a surface. And the way that I'm going to generate a surface is that I'm going to take this curve as my one cross section, and I'm going to build a surface that starts from here and moves in this direction like this, right? And it's the one end of this surface is going to be exactly this curve. So this curve is going to be just one cross section of it, and I'm going to build a surface from this curve. And for that, I will need 4 other curves. Why do I need 4 other curves? Because I'm going to do something. I'm going to do the exact thing I did for generating this one curve. So for generating this one curve, I formulated, my Bezier formulation was just the weighted average of these 4 control points, right? So Bezier formulation is some way of generating a weighted average of 4 points in space. Now, for generating a Bezier patch, I'm going to take 4 Bezier curves, and I'm going to form a weighted average of 4 Bezier curves. And the weighted average of these 4 curves is going to give me the surface. Now, for generating a Bezier patch, I'm going to need 2 parameters. One parameter is going to tell me where I am along the curve, along each one of these curves in this direction. The other parameter is going to tell me where I am between these 4 curves. So I'm going to have, let's say, a t parameter in this direction, and I'm going to have an s parameter in this direction. So there's going to be 2 parameters. Again, they're going to be parametric polynomials, but those parametric polynomials will have 2 parameters instead of 1. All right. So are you ready? I'm going to take these 4 curves, and first I'm going to place them wherever I want in space. Let's say that I want to move them like this. All right, that's where they are. That's where I want my curves. And from that, from these curves, now I have these curves. I'm going to now connect them. So this is creating my control polygon for my Bezier patch. And this control polygon that contains 16 control points is going to define this lovely Bezier patch. This was, back in the day, this was a very, very convenient way of producing models. We don't always generate models like this today. We prefer other methods, but this is still a way of generating 3D models. Good catch. Someone mentioned Utah teapot? Yes, there it is. The famous Utah teapot, the symbol of computer graphics, is actually a collection of Bezier patches. This is the original notes for generating those control points that was drafted to build the Utah teapot, and then Jim Blinn took it and squished the teapot a little bit. That's why the shape looks a little different. Now, there's a history of that in our graphics website, graphics.cs.utah.edu. So check it out if you're interested. But yeah, the Utah teapot is an example of a Bezier patch, a collection of Bezier patches. It actually contains multiple Bezier patches. So we have our lovely teapot. That's not necessarily a popular method for defining surfaces in computer graphics today. We have more popular methods. Talking about popular methods, one method that used to be very, very popular, is still used in practice today, is NURB surfaces. We talked about them last time when we were talking about NURBs. NURBs are non-uniform rational B-splines. So it's just another way of combining averaging points together. You can do the same thing we did with Bezier patches, and this time we're getting a NURB surface instead of a Bezier patch. Exactly the same idea, with just a different formulation. Instead of using a polynomial that in Bezier formulation, we're using a rational polynomial with non-uniform parameterization. And then we get these surfaces. Of course, NURB surfaces, we talked about them, they don't interpolate the control points, so they don't go through any of the control points. Although you can force them to go through the first and the last control points in your formulation. We looked at these examples. I'm just showing you the same examples, some models generated using NURB surfaces, even relatively recent models used in production, generated using NURB surfaces. But the probably the most popular method for preparing 3D models today, or 3D surfaces today, is using polygonal meshes. So here's an example of polygonal mesh of this model of an elephant. You're seeing two different polygonal meshes here with different resolutions. We call them resolutions, the number of polygons we have for representing the model. And as you can see, these polygons are, we have some quads, and we have some, I believe we have some pentagons here. We have some triangles. So polygonal meshes are a collection of different types of polygons. Of course, they don't have to be low resolution like this. We can have a lot more polygons for representing our surface. And the more polygons we have, the more details we can represent on the surface. That's the main idea. So this turns out to be the most popular way of generating 3D models today, right? So when we think about a polygonal mesh, it's made out of, obviously, polygons. And each polygon would have a number of vertices and the same number of edges, right? And they're connected by sharing vertices and edges. Each polygon forms a small piece of the surface. And this is the structure we prefer using in computer graphics. But this is a computer graphics course, so we kind of need to talk about the data structures just a little bit. At least just a little bit. So let's do that. So what do I do for representing a polygonal model like this? It turns out, at the very least, I need to know where these vertices are in space. Right? I need to know the 3D positions of these vertices. And I also need to know how these vertices are connected, like how the polygons are formed out of these vertices. That's the minimal information that I need. Now, there are different ways of storing this information. So the most convenient way of storing this information is like this. I have a list of vertices and XYZ coordinates per vertex. You can have other information per vertex. Remember we talked about vertex attributes when we were talking about WebGL rendering? So we can have other attributes that we can store per vertex, but at the very least, I need to know where a vertex is in space. And I also need to have a list of polygons, and each polygon would have a list of vertex indices. And from these vertex indices, I can form that polygon. We oftentimes call them faces. Well, some people, when they call faces, they refer to triangles specifically, but I often use them as faces are polygons. Faces. When I say a face, what I mean is just a polygon of a polygonal mesh. That's what I mean. So this is what we need at the very least. Well, what happened to the edges? Well, we talked about edges in the previous slide, right? So where do they go? Well, they're not represented here. So turns out we don't really need edges very often. Although, there are certain modeling operations that people like to use that involve edges. So in some cases, it becomes convenient to store the edges as well if you want to. So you can store the edges as well. They're not necessarily required. Actually, just using the polygon vertex indices and list of vertices, you can form that mesh. And then from that, you can generate a list of edges. And you can add edge indices to the polygons. So this part is not necessarily required, but for certain algorithms, it becomes very convenient to actually explicitly store this, like a list of edges, edge indices, and the list of edges that contain the edge data. That might be very, very convenient for some applications. So sometimes we do store them. Actually, there are some famous data structures that are also mentioned in the book. For example, the winged edge structure. The winged edge is like an edge with wings. Think about it that way. So I have this edge here. That edge is connecting two vertices, so it's going to have access to those two vertices. And it is also connecting two faces. It's two wings. So it's going to have these two face indices. I said one or two face indices here because this edge might be the end of a surface. If it's the end of a surface, then one of these faces may not exist. So if this face does not exist, then it's going to only have one face. If this first does exist, then it's going to have two faces. Yeah, so this is the winged edge representation. It's a very convenient representation for certain algorithms that walk over the mesh, to apply certain operations, to perform certain operations. This winged edge representation can be very, very convenient, and sometimes we do store that. Sometimes people prefer a slightly simpler representation because the thing here is it's like I'm duplicating data, right? I'm like storing things multiple times, and for a lot of algorithms that may not be really necessary. There's a simpler structure, simpler equivalent edge structure that people like using. That is the half-edge structure. The half-edge structure would just store one half of the edge, one half of the winged edge. So it's going to store one vertex and one face. It's not going to store the other edge. So in the half-edge structure, I'm going to have a corresponding edge going in the opposite direction for the other face, for the corresponding face. And oftentimes I'm going to have some way of addressing the corresponding edge of a half edge, corresponding half edge of a half edge. That's going to be right over here in this direction, pointing to this vertex. And combining this edge representation with all sorts of vertex and face representation, you can form various ways of storing a polygonal mesh data. And what exactly you store really depends on what kind of algorithms that you want to run. At the minimum, you will need some way of representing vertex positions. That typically means you're going to have a list of vertices. And oftentimes you're going to need a list of vertices per face or per polygon. Although that's not strictly required, because there are ways to construct this from a half-edge structure or a pure half-edge structure or a winged edge structure, but it's typical to store a list of polygons as well. And for certain algorithms that walk over the mesh, you may need to store the edges as well, if you need to. All right. And we're going to talk about more of this next time in a bit more detail. Not about edges, but list of faces and list of vertices. So I said turns out that people like this. And a lot of people that do modeling in computer graphics really prefer working with polygonal meshes. And so this is the most commonly used data structure that we have. By data structure, I mean in general, any way of storing these polygonal meshes. This polygonal mesh representation is the most popular surface representation we have in computer graphics. So here's an example of polygonal mesh modeling. As you can see, by doing all sorts of polygonal operations, you can generate interesting models. Well, I hope you find this model interesting. If you don't find it too interesting, I'll show you another one. Here's another one using very different operations. And just some operations are just moving vertices around. Some operations are just adding faces. So as you can imagine, yeah, the polygon mesh is our data structure, but there are many ways of modifying a polygon mesh or building a polygon mesh, right? And there are all sorts of tools out there with all sorts of capabilities. And if you're interested in polygon modeling, it would be a good idea to be familiar with a large collection of tools so that you can use the right tool for exactly what you're trying to do. And yeah, this is a computer graphics course, but this is not a modeling course, so I'm not going to get into details of any particular modeling operations that are showcased here. But I just want to show you that there are various ways of there are numerous ways of fiddling with a polygonal mesh, and depending on exactly what you want to do, they have different advantages that you may want to be familiar with if you want to do anything like this. But you can think about, the simplest operation is, select a bunch of vertices and apply some affine transformations to them, like move them around or rotate them around some point or scale them, or add more polygons, add edges on the surfaces of polygons, delete polygons, delete vertices, all sorts of a very, very large collection of low-level operations and operations that combine various operations together to form a higher-level modeling operations. But nonetheless, when you look at this, you should recognize that preparing a 3D model like this is actually quite labor-intensive. So it seems like using like Bezier patches or even implicit surfaces might be quite a bit easier than all this, right? But people do prefer this, and there's a good reason for that. And the main reason, I think, is that because this gives you very precise control, you can directly control the surface. With, for example, implicit formulations, it becomes quite tedious. You kind of need to understand those equations really well. And even when you do understand them, it may be very difficult to control them exactly how you want to. But with this, it's quite intuitive. You deal with your problems with one vertex at a time, and that kind of makes this controllable. Nonetheless, I would say, you look at a model like this, and you can imagine, okay, this is going to take me quite a bit of time to prepare a model like this, right? I mean, you look at this. There's so many vertices here. If I want to generate a model like this, I'm going to spend it. It's not going to be trivial, right? If I show you this and say, okay, now I'm going to take it away and say, go model this and pick the vertex positions for this mesh and generate the whole polygonal model. That's going to take a very long time, right? And this is not a very impressive model. It has actually very few polygons when you think about it, and the surface is not very smooth. So imagine modeling something more like this, which has a lot more polygons in it. It's a lot more work. So yeah, preparing polygonal models, actually, I would like you all to appreciate this process. It's not easy. Yes, we do have tools. We have a whole bunch of tools. But nonetheless, we have a lot of vertices to deal with and a lot of vertex positions to be concerned about. So preparing that is not going to be that easy. And the other thing is that it's not just about moving these vertices around. I also need to create all of these polygons, right? Connect all these vertices together and form these polygons. That's not going to be very easy. But that part turns out we have some very nice tools to help us with that. And that brings us to the concept of subdivision. So subdivision is the process where we get a low-resolution mesh, and from that low-resolution mesh, we automatically generate a higher-resolution mesh. Technically, not everything you do to generate a high resolution mesh from a low resolution mesh would be technically subdivision. Subdivision has certain limits, but subdivision or certain more specific definition. Nonetheless, subdivision is the process with which we generate high resolution surfaces, high resolution polygonal meshes from low resolution polygonal meshes. Now, I'm showing this as an example of subdivision, but I don't believe in this case this is pure subdivision. This model probably generated from this low resolution model using subdivision, and then it got modified a little bit. I'm noticing a few topological modifications. By topological modifications, I mean the way that vertices are connected together is modified here from typical subdivision operations that I'm familiar with, especially over here. There are some polygonal shapes that I wouldn't expect to see from a pure subdivision. So, yeah, this is probably not a good example of subdivision. So there are various subdivision techniques out there. People came up with various mathematical models for taking a low resolution mesh and generating a higher resolution mesh out of them using some sort of subdivision operation. There are various subdivision models out there, but there is one that is very popular. And when people talk about subdivision without saying what kind of subdivision they're talking about, they are talking about Kaplan-Clark subdivision almost always. So when people talk about subdivision, and if they don't tell you what subdivision method they're talking about, they're probably talking about Kaplan-Clark subdivision. So if these names sound familiar to you, Ed Catmull and Jim Clark, back in the day, they were in University of Utah, and they came up with this subdivision technique that is pretty much the way that we generate models in computer graphics today.
So here's how it works. Given a polygonal mesh like this, I'm going to generate a higher resolution polygonal mesh out of that, all right? And the way I'm going to do this is that for each face of this polygonal mesh, I am going to generate more smaller faces. So for each face, I'm going to split it into multiple faces. This is an operation that we call tessellation. So I'm going to tessellate each face, each quad face in this case, into 4 quad faces. And then I'm going to move the new vertices around to get this sort of rounder, smoother shape, right? So the way this is going to work is that it's going to generate a vertex at the center of each face, right at the center here. And then it's going to generate vertices at the centers of the edges. Then it'll move those edge vertices towards the average of the neighboring faces. And then it's also going to move the vertices, the original vertices around the corners here, towards an average of the neighboring faces and neighboring face vertices and neighboring edge vertices. But I'm not giving you the exact formula. The exact formula is very simple, but it's not that important. The important point is that I am getting a higher resolution and smoother surface. So if I apply the very same Kaplan-Clark subdivision rule again, I am going to get a higher resolution model looking like this, right? And I can keep doing this, right? I can get a higher resolution surface and then a higher resolution one and a higher resolution one. And in the end, this is going to approach to a limit surface like this. Right? This limit surface, the nice thing about that limit surface is that it is provably C2 continuous, except for the extraordinary points. But most of the surface is going to be C2 continuous, which is great, because C2 continuity will produce really nice looking, smooth, continuous looking reflections on surfaces. So we want to have C2 continuous surfaces when in computer graphics. And the only place where C2 continuity sort of breaks and it becomes C1 is these extraordinary vertices. How do I say? These are vertices that don't have 4 edges coming out of them. So for all vertices here with 4 edges coming out of them, they're going to be fine. But if there's a vertex that has less than or more than 4, like the corners of the original vertices are actually of the cube have just 3 edges coming out of them. So yeah, they're going to be extraordinary vertices. We're not going to have perfect smoothness around points. So this resulting surface looks like a sphere, but it's actually not a sphere. It's sort of sphere-like shape, but it's not a perfect sphere at all. Nonetheless, it's a very nice and smooth surface that we like. All right. It depends on what you start with, though. So if you start with a cube, this is what you get. If you start with a cube that has this sort of mesh connectivity, this is what you get. But if you start with the same shape, but a different mesh connectivity, what different mesh representing the same shape, Kaltman-Clark subdivision will approach to a different looking surface. Like in these examples, all of the ones above are cubes with different polygonal meshes representing cubes. And then you get the resulting shape you get with Kaltman-Clark subdivision would be different. Now, I've been showing you just quads. Kaltman-Clark subdivision can be applied to triangles as well. If you apply it to a triangle, you'll get 3 quads. If you apply it to a pentagon, you're going to get 5 quads. So in the end, you're going to get a quad mesh out of whatever kind of polygonal mesh you start with. But you probably want to start with a quad mesh because Kaltman-Clark subdivision works really well with quads, doesn't work as well with triangles and pentagons and other kinds of polygons. Let me show you an example. Here, if I start with a mostly quad mesh, we call them quad dominant mesh. There may be some triangles in them, but it's mostly quad. A quad mesh would, when you apply Kaltman-Clark subdivision, you get something that looks really smooth and nice. Now, if you triangulate this, this is a triangular mesh. All the faces are triangles, not quads. In this case, again, I'm getting a smooth surface, but it kind of has these sort of wiggles on the surface that doesn't quite look like this, right? You should be able to see that the surface is, it's still smooth in the sense that it is still C2 continuous, but the shape is a little bumpy because of these original triangles in there. So that's why when we're modeling things, we prefer to use quad dominant meshes that are mostly made out of quads, maybe some triangles here and there, because if you're just using quad meshes, that will sort of restrict the topology quite a bit, the mesh connectivity quite a bit. So you may want to add a few triangles here and there to get the mesh topology, basically the connections between vertices, to get the mesh topology that you want. You may want to squeeze in a few triangles here and there. All right, so there's an example model, and after the Kaltman-Clark subdivision applied to it, so if I remove the low resolution mesh, you see that it looks smooth. So this is just displaying the edges of the low resolution mesh on this smooth surface after we apply Kaltman-Clark subdivision. So when we're trying to model a high resolution model like this, when we're trying to produce a high resolution model like this, we typically start with a low resolution model, and then we apply a subdivision to it. Typically, it's Kaltman-Clark subdivision to get a smooth-looking surface like this, right? But wait, the original model I showed you had quite a bit more details. Oh yeah, this looks smooth, but beyond looking smooth, it doesn't have the details that the model that I wanted have. Like, it doesn't look like this, right? So how am I going to add these small-scale details? Well, I can actually, but of course I'm going to be dealing with a mesh with a lot more vertices, right? So I can apply Kaltman-Clark subdivision, and then if I want to change the mesh connectivity, mesh topology, I can do that. I can edit that, and then I can apply Kaltman-Clark subdivision again and again, and then in the end I'm going to get a smooth-looking surface and with a lot of vertices, and then I can move those vertices around to add these small-scale details. And for that, we have tools that are specialized for adding these small-scale details. ZBrush is a very popular example that allows you to sort of paint on the surface and add these bumps and dents on the surface so you get the high-resolution details that you want, right? So you can use tools like this to deal with super high-resolution models in the end. But we start with a low-resolution model, and then we typically apply multiple levels of subdivision to get a high-resolution model like this. And then the high resolution models are sort of modified using different types of tools. So that's the general idea of how we generate high-resolution models in computer graphics. In the end, though, most of these polygonal models are converted to triangular meshes for rendering, because rendering operations are a lot easier when you're dealing with triangles than with other types of polygonal meshes, like quad meshes. The reason for that is that a quad does not have to be planar. A triangle is always planar because 3 points in space would define a plane. But for a quad, the 4 vertices of a quad, they don't have to be on the same plane. So if they're not planar, as a primitive, it's a lot harder to deal with. So that's why we take all of these polygonal meshes and convert them into triangular meshes before we render them. And that's very easy to do. Like given a quad, I can easily convert a quad into 2 triangles like this. But actually, there's more than one way of doing this, right? So I can triangulate my quad like this, or I can triangulate it like this. Either way, but they're both okay. So which one would I pick? It's really hard to choose because, I mean, they look the same. It's as if it doesn't matter. But in 3D, it would matter because, especially if these 4 vertices are not on the same plane, if they're not planar, then the 2 triangles you will get out of them would look a little bit different, right? These are not the same shapes, right? They're different shapes. So triangulation might matter. So that's why we sometimes leave this to the user. So you can specify how you would like your polygonal mesh to be triangulated. Nonetheless, we can apply triangulation to all sorts of polygonal meshes. And if you have a pentagon like this, of course, you're going to have more ways of triangulating it. But nonetheless, given a model, we triangulate it and we render them that way. This is not specific to polygonal meshes. Actually, remember we talked about this guy? Originally defined as Bezier patches? Yeah, so we can take that, we can take those Bezier patches and we can triangulate them. We can generate triangles out of them for rendering purposes. Now, this is a relatively low resolution version of the Utah teapot. Of course, you can generate a high resolution version as well. It will be represented by a bunch of triangles when we're rendering them. So we're going to talk about, because of that, we're going to talk about triangular meshes in quite a lot of detail next time around. So our next lecture for this course will be all about triangular meshes. Thank you all for joining another lecture for Introduction to Computer Graphics, and I'm going to see you all next time. Bye.